Hello, my name is Scott Bryson, and I am an applications engineer for the Texas Instruments current and position sensing product line. In this video, I will provide a quick recap on Hall effect latches and take a deeper dive on two-dimensional latches by covering the functionality, underlying properties, and typical applications. As a quick recap, a Hall effect latch indicates the most recently measured magnetic flux density, and alternating north and south poles are required to toggle the output of latch devices. For the purpose of this discussion, we will refer to this as a one-dimensional or 1D Hall effect latch. These are typically used in rotary applications such as brushless motor commutation and incremental rotary encoding. As shown in our previous videos in this series, here is the output graph of a traditional Hall effect latch. Applying a south magnetic pole near the top of the device in excess of the operating point known as BOP causes the output to be driven low. It will remain in this state until presented with a north magnetic pole with an input to exceed the release point known as BRP, at which point the output will return to the high state. Similar to the case before, the output will remain high until the south pole is presented to the sensor again. An absence of magnetic input will always result in the last latched state remaining active. Finally, the hysteresis range, BHYS, refers to the range between BRP and BOP. Since we cannot visually observe magnetic fields, it can sometimes be difficult to imagine the directionality of a magnetic field vector. Here we can see a two-dimensional slice of the field produced by a cylindrical magnet. Notice that along any of the represented field lines, that the direction of the field vector curves and will vary both positive and negative for each axis represented. Depending on the sensor location used, a different polarity and magnitude of the magnetic flux density would be observed in the sensor. For many applications, such as quadrature tracking for rotation, speed, and direction, angular measurements, and multi-directional motion, as a few examples, there is simply not enough information that can be captured by one sensing element to properly characterize the motion of the magnet. For instance, if the magnet pictured above were to move horizontally, we could not distinguish whether that motion was to the right or the left. The sensor is only sensitive to the component of the vector directed vertically, and due to symmetry, this will be the same for equal steps to the right or left. As a result, 1D sensors will require that multiple sensors be placed in the system to capture this kind of information. 1D Hall effect latches may be used in incremental rotary encoding, but this requires two devices. One latch can be used to determine the speed of the motor, while a second latch can be added with a phase offset, which will produce greater resolution and enable detection of rotation direction. Creating this phase offset requires appropriate spacing of the sensors. An ideal 90-degree quadrature offset is attained when the sensors are separated by half the length of each magnet pole, as shown here, or at any integer number of pole lengths. As an example, we can observe quadrature output at both 22.5 degrees and 67.5 degree separation using this 8-pole magnet. As the magnet rotates, we will observe a change in output for each incremental rotation of 22.5 degrees, and we can determine the direction of rotation based on the phase of the output change. For more information on designing incremental rotary encoding with 1D latches, check out our videos on latches and switches, or using Hall position sensors for rotary encoding. Consider briefly a field produced by a multi-pole ring magnet. Typically, these magnets are polarized radially outward. On the left is a top-down view of the field vectors in plane with the magnet. We can see that the vectors emanate outward from the positive or red faces and curve back inward toward the negative blue faces. This is fairly simple to visualize when considering a magnet of this type. What becomes more challenging is to conceptualize the field when a vertical component is introduced. On the right is a cross-sectional slice through two opposing negative poles as viewed from the side of the same magnet. Notice that within this plane, that the field vectors also wrap around the top and bottom of the magnet. As a result, we can observe that at all locations around the magnet, the field vector will actually have components in 2 or 3 axes, and that the behavior of the field vector components will be sinusoidal in nature. As we have just shown, 1D latches have a single hollow element at the center of the device, which is sensitive to magnetic fields perpendicular to the face of the package. Once soldered onto the PCB, a through-hole package or surface mount package each offer a unique sensing direction, and sensing capabilities are defined by mechanical constraints of the application. Because 2D latches have hollow elements which are orthogonal or rotated 90 degrees from each other, and can measure components in 2 different directions, they offer a wide range of mechanical configurations. 3 sensitivity combinations are possible: XY, YZ, and ZX. With the increased visibility of the magnetic field within a single device, the result is greater design flexibility and improved measurement accuracy. Understanding the field behavior with multipole ring magnets makes 2D latches a practical choice. These magnets are commonly available in either sintered or bonded varieties using various magnetic materials. 2D latches are ideal for applications leveraging rotating ring magnets such as quadrature detection, and are also targeted to support incremental rotary encoding applications. The profusion of rotary encoding applications using 2 latches for best performance has created a market for a device that has 2 latches in a single chip. However, as discussed previously, the placement of the 2 latches is important relative to the count of magnetic poles in the ring magnet. An alternative to the 2-dimensional sensor is the 2-channel latch or dual latch that has both sensors coplanar. This type of device is faced with mechanical alignment limitations, including the IC to magnet placement and the magnet pole pitch versus Hall sensor separation. Accurate performance will require that the 2 sensors be physically 90 degrees separated. This means that the magnet poles must be small enough to match the sensor separation, or that the sensor package must be large enough to accommodate the pole spacing. Small magnet poles produce less magnetic field, which may not be adequate to trigger the sensor, and large devices defeat the benefit of a single chip solution. In order to determine the direction of rotation, there needs to be distinct quadrature of 2 sensors relative to the magnet poles. With an ideal quadrature alignment, we see that the 2 outputs are 90 degrees out of phase. However, if the pitch between sensing elements is not separated adequately, the quadrature error increases significantly, and incremental steps will be uneven. This highlights how an imperfect mechanical arrangement of magnet pole pitch will adversely affect the performance of your rotary encoding application. Magnet imperfections, including pole size and field strength variations, further complicate the ability to accurately distinguish incremental position changes. To optimize the pole switch point requires the pole pitch to be 2 times the separation of the 2 planar sensors, or rather, that the separation between the Hall elements be 1/2 the pole pitch. This challenge is precisely why orthogonal sensing elements are ideal for a single package solution. By sensing vectors which are naturally 90 degrees out of phase with each other, the Hall elements are then optimally placed as close to each other as possible for the best result and smallest package size. Again, 1-dimensional Hall effect sensors require the 2 devices to be spaced such that the outputs are electrically 90 degrees apart. Here we can observe both the direction and speed of the rotating magnet based on the frequency of pulses and the order of rising and falling edges. 2-dimensional latches have the option to select each of the possible Hall element combinations within the device. The selected components are brought to the interfaces for signal conditioning. The different magnetic field components are inherently 90 degrees out of phase, and this produces an equivalent result to the 1D sensor. A major benefit to this approach is that alignment accuracy is integrated, and the total mechanical area in the solution occupies is reduced dramatically. Additionally, a 2D latch may also integrate the computation to generate outputs formatted as speed and direction when monitoring incremental rotation. With the new class of 2D latches, the 90 degrees phase relationship of the two Hall sensors offer inherent quadrature for rotary encoding applications, overcoming the limitations of dual latches with planar elements or the use of two 1D latches. TI's family of 2D latches offer three two-axis sensing options: XY, ZX, and YZ. The different sensing directions allow a variety of sensing configurations, including off-axis placements. TI offers 2D Hall latches in addition to the standard one-dimensional latches. Among these are TMAG 5110 and TMAG 5111. TMAG 5110 has two independent outputs similar to the output produced by two 1D latches. TMAG 5111 integrates on-chip decoding of the dual Hall latch outputs to provide both the speed and direction output information instead of the raw Hall sensor outputs. The direction of rotation is easily determined by tracking the change in phase alignment of the two input components. Here are a few examples of applications for 2D latches in the automotive and industrial market. For automotive, the small body motors and power closures throughout the car, specifically in windows, sunroofs, lift gates, trunk lids, sliding doors, and power seats. For industrial, there are garage door openers, thermostat dials, or any knobs and dials in white goods, the wheel rotational sensing of a vacuum robot or a robotic lawnmower, and motorized window or door blinds, to name a few. Again, we encourage you to explore the various materials we have available on TI.com regarding incremental rotary encoding using 2D latches. First, we have the TMAG 5110 5111 EVM with LED displays showing the output of both the TMAG 5110 and TMAG 5111. The evaluation board allows two different placements of a multipole magnet. LED display can indicate both the actual output state of each device as the magnet rotates, as well as provide indication for incremental decoding. Next, we have two publications which discuss design considerations for incremental rotary encoding using Hall latches, 1D and 2D. These are incremental rotary encoder design considerations and reducing quadrature error for incremental rotary encoding using two-dimensional dual Hall effect sensors. Each explores the subject of incremental encoding with more detail and provides guidance to optimize performance. And as in all cases, we recommend taking a look at the device overview and application sections of the datasheet for more technical information of device functionality, magnet behavior, and how to implement rotary encoding in your system. For more information on TI's 2D Hall latches, please visit ti.com/Hall effect to explore our Hall effect latch and switch portfolio and resources, or visit the TMAG 5110 and TMAG 5111 product folders directly. We also invite you to attempt the quiz to check your understanding of this video's content.